In this lecture, we will discuss about automorphism of a group. So, automorphism of a group. When we understand about homomorphism, isomorphism, endomorphism, then next topic is automorphism of a group. So, for defining automorphism, we take as let G be any group which satisfy all four properties of group, and function f which is defined from group G to G, means same group G to G, which is 1 1 and on 2, which is 1 1 and on 2. So that means we have a group G. So this is group G, and another we also group G function defined as 1 1 and on 2, where each element of set A related to unique element of set B, and every element of set B has a pre-image in set A. So which is 1 1 on 2 and satisfy the definition of homomorphism. That means FAB is equal to FA into FB. So then F is called an automorphism. F is called an automorphism. Now we move to the next definition, that is inner automorphism. So there are two types. One is inner automorphism, second is outer automorphism. So which do not follow the inner automorphism, that is the outer automorphism. So for defining inner automorphism, we take same definition. Let G be any group. G be any group, and A be the element of G. So then the function, or we can say mapping, we defined as FA such that from G to G, for every we take X be the element of G. So then FA of X is equal to A inverse XA. So is called inner automorphism. Is called inner automorphism. So this we take question mark. This is inner automorphism or not? For proving inner automorphism, we need to prove that this function FA satisfy the properties, that is 1 1 on 2 and homomorphism. So now let us prove this FA is inner automorphism or not. So for proving this, so we write down as, so first we shall prove that FA is 1 1. FA is 1 1. For proving FA is 1 1, we take two elements, let X and Y be two elements of set G or group G. So then for proving 1 1, so we take as FAX is equal to FAY. So we take as normally when we proving the 1 1 function, so we take as Fx equal to Fy, now to show that X equal to Y. So similar thing we will do here. So we take Fax equal to Fay. So by the definition of in Fax, so Fax is A inverse into Xa is equal to, here we write A inverse Y into A. So this we write down as by definition, this definition. Now we use the using left and right left and right cancellation law. Left and right cancellation law. So we can write down as x is equal to y. So when x equal to y, this shows that only a single element. So we can say that fa is 1 1. So when we have proved fa is 1 1, now to prove that fa is onto. So to prove that fa is onto. So for proving fa is onto, so we take a element of set B. Set B means set G. So both are G. From G to G function is defined. So let basically we understand in this way. So this is our x, this is y. So here we have element of x belongs to x and a small y belongs to y. The mapping we defined from x to y. So this can be written as function is defined from x to y. For proving onto function, so we take this element, we take y belongs to y and show that it's having the preimage in x. So we take as let y belongs to g, because function in this defined from g to g. So function is defined from g to g. So we take y be the element of this group and we show that it have preimage in set g, also this set. So y belongs to g. So then there exists an element. There exists an element. Element. So which element belongs to this g? So any element. So we can write a y a inverse. A y a inverse belongs to g, such that so we write down f a in place of x we put as a y a inverse. So this equal to the definition is a inverse x a. So in place of x we put this thing. So we write down as a inverse into x. In a place of x we write down a y a inverse into a. So this can be written as a inverse into a y a inverse into a. So a inverse into a is equal to e. So e y into e or e y into e gives us y. Or this y belongs to g. So it means that this y having the pre-image. So FA is onto. FA is onto. So hope you understand. If not understand, so how to write this element? So we can elaborate this here. So we take as A inverse. So we have the function A inverse into XA. So fx equal to y, you know. So when y is equal to function of x, so we can write down a function of x. So we have x inverse, the a inverse into x a. A inverse x a is equal to y. So this equal to f a. So f a means y. So this equal to f a y. So now we post multiply both side by a inverse. So post multiply both side by a inverse. So this gives us this. So a into a inverse equal to identity. So a into a inverse equal to identity. So this can be written as in this form. Now pre-multiply both side by a. So pre-multiply both side by a. So x into e equal to x. So we can write down this as y pre-multiply by a. So into a inverse. So uh, a inverse into a is also identity. So e into x is equal to a y a inverse. So e into x equal to x. So x equal to a y a inverse. So this x equal to a y a inverse. So that's why we write down this as a y into a inverse. Okay, hope you understand. Now, when fa is onto, so we shall prove that fa is homomorphism. So to prove that, again, to prove fa is homomorphism. Fa is homomorphism. So for proving Fa is homomorphism, so again we take two elements. So let x and y be two element of group G. So then Fa Fa of xy is equal to Fa of xy is equal to function is defined as, so we Function is defined f(a) equal to a inverse into xa. So now this can be written as a inverse into x replaced by xy into a. So we write down this as, so this equal to a inverse. So a inverse xy. So xy can be written as x e into y a when we. So now this can be written as a inverse into x, or this e can be written as a into a inverse. E can be written as a into a inverse into ya. So a into a inverse is equal to a inverse a equal to e. So now this can be taken as from one side, this can be taken another side. So we can write down as a inverse into xa, or second is a inverse into ya. So by definition of function, which is defined as, so this can be written as fa of x into fa of y. So fax into fay. So it is clear. So function fa is a homomorphism. So it is clear, function fa is homomorphism. Fa is homomorphism of group G. So then it is inner automorphism. Now we have one important theorem related to that. So we shall move to this theorem. So prove that the set of all automorphism on a group is again a group under the operation as composition of functions. Composition of functions. So we shall prove this theorem. So prove that the set of all automorphisms on a group is again a group. So we can take as, so let G be any group, and let automorphism of group G, which is defined as f, function f, such that f is an automorphism. F is an automorphism. That means which is 1, 1, onto, and homomorphism of group G. So to prove that automorphism of G is a group, is a group. So for proving this is a group, so that means we satisfy satisfy all the properties of group. That means closure, associative, identity, and inverse. So now we start with the first property, that is the closure property. That is the closure property. So for proving the closure property, so let we take two element of group G. So that means A and B belongs to G. So AB also belongs to G. So here we take a composition of functions. So we take two functions that may be defined as f. So let f and G be two functions which belongs to automorphism of a group G. So then when it is automorphism, so it is automorphism. So it is clear. So that is, we can write down as, that is the function f, which is 1, 1, already 1, 1, and onto, and homomorphism. Also G is 1, 1, onto, and homomorphism. So because F is automorphism already given in the function, so we can take two elements and F and G. So both are already 1 on 2 and homomorphic. So we claim that G composition F, which is defined from G to G, is an automorphism. So for proving G composition F is an automorphism, so it means that we shall prove that G composition F is 1, G composition F is on 2, and G composition F is homomorphism. So here we have a group G, so we define for G, so that means this function defined from F, G to G, and here we define from G, from G to G, small g, and from this to this we can define as from G composition F, from G to G also. So now when we shall prove that G composition F is automorphism, so it is clear, we shall prove that G composition F is 1. So G composition F is 1. So G composition F is 1. So we can take G composition F of X is equal to G composition F of Y, two elements. So that means proving 1. So this can be written as G of Fx. G of Fx equal to G of Fy, or F and Y. Or first we take as G of Fx and G of Fy. So G is already 1. So G is 1. So when G is 1, so this can be written as Fx equal to Fy. So Fx equal to Fy, or F is already 1. So F is 1. We assume that F is 1, G is 1. So this can be written as X equal to Y. So when X equal to Y, so it means that G composition F is 1. So G composition F is 1. Now after proving G composition F is 1, so we shall prove that G composition F is on 2. So for proving G composition F is on 2, so second we write down as B part. So G composition F is on 2. So when we shall prove the G composition F is on 2, so we take the element Z which belongs to G. So Z means third element. So here we consider as X, we consider here as Y, and we consider as Z. So third element, so we consider as Z belongs to G. So small z we can write down as. So Z belongs to third set. So that means since we can define as G, small g is function from G to G is on 2. So it means there exists an element, Y. So Y is also belongs to G. So this can be defined as G of Y is equal to Z. Now we have a F from G to G is on 2, which is already given in statement, so which is on 2. So that means for every Y belongs to G, this means from this set, so then there exists an element X which belongs to this set. So X belongs to G such that F of X is equal to Y. F of X equal to Y. So then we can write down as Z is equal to GY. So then we can write down as GY. Y means F of X. So G of Fx. So G of Fx can be written as G composition F of X. So we can write down as G composition F of X is equal to Z. So that means Z having pre-image in Y, or Y having pre-image in S. So G composition having a pre-image, that means X. So G composition F is on 2. So G composition F is on 2. Now we shall prove that G composition F is homomorphism. So C part, so G composition F is homomorphism. G composition F is homomorphism. So for proving G composition F is homomorphism, so we can take a G composition F of AB. So we take two elements. So this can be written G of FAB. So this can be written as G because F is homomorphism. So F is homomorphism. We can write down FA into FB by definition of homomorphism. So here we write down as F is homomorphism. So now G is also homomorphism. So this can be written as G of FA into G of FB because G is also homomorphism. So G is also homomorphism. So G of FA can be written as G composition F of A and G of FB can be written as G composition F of B. So G composition F of B. So we write down as G composition F of B. G composition F of B. So this can be written as G composition F is homomorphism. G composition F is homomorphism. So we can say that G composition F belongs to automorphism of G. Automorphism of G. So then satisfy the closure property. So now we move to the second, that is the associative property. So for proving associative, so we can say that since f of gh, we take three functions, so then this satisfy fg of h. Because we say that associative property is a hereditary property, so always hold for each case. So that means uh, we can write down for any type, for any types of function, it holds. So there is no need to prove this. So this it holds for automorphism also. It holds for automorphism also. So there is no need to prove this associative property. Associative and commutative are hereditary property that always hold for each case. Now we move to the third property. So first we prove the existence of inverse before the identity. So we shall prove that existence of inverse. So proving existence of inverse. So let we take as function f which belongs to automorphism of A of G. So which implies that function is 1 1, function is 1 1, function is on 2, 1 1 on 2 and homomorphism. F is 1 1 on 2 and F homomorphism. So then we have one theorem in function, a function which is 1 1 as well as on 2. So then that type of function possesses the inverse. So that type of function possesses the inverse. So it is clear. So when function is 1 1 and function is on 2, when a function which is 1 1 as well as on 2, so such type of function possesses the inverse. So then we can write down as f inverse of such functions is exist also. So when f inverse of from G to G, so which is 1 1, which is 1 1 on 2 and f inverse is homomorphism. So we need to prove that means f inverse is homomorphism or not. So basically it's also 1 1 and on 2, but this is also f inverse homo. So now we shall prove that f inverse is homomorphism. Homomorphism. So for proving homomorphism, so we take as let A dash and B dash be two element of G, but the function f which is on 2 and 1 1, function is on 2 and 1 1. So we can take that there exist two elements there exist two elements A and B which belongs to G, such that FA is equal to A dash and FB is equal to B dash, because function is 1 1 and on 2. So we take the diagram as, so G to G, here we have AB, here we have A dash B dash, function defined from G to G. So we can say that function is 1 1 and on 2. So FA equal to A dash and FB equal to B dash. So now we take F inverse of A dash into B dash. So F inverse of A dash into B dash. So this can be written as F inverse of A dash. So A dash can be written as FA and B dash can be written as FB. So this equal to, we can write down as F inverse. So FA and FB, by using the definition of homomorphism, can be written as FA into B. So because F is homomorphism, so we write down this as, so F inverse into F. So when F inverse into F, you can write down F inverse into F into AB. So this can be gives as AB. So AB, so this AB, so when function A equal to A dash, B equal to B dash, so when we write down this as inverse function, so this gives us F inverse A dash equal to A, and this gives us F inverse B dash is equal to B. So we can write down in place of A, that is F inverse into A dash, and in place of B we write down as F inverse into B dash. So F inverse into A dash B dash equal to F inverse A dash into F inverse B dash. So it means that F inverse is homomorphism. F inverse is homomorphism. So only we need to prove that, means F inverse is homomorphism. Also, if you want to prove the F inverse is 1 1, so we can also prove that. So for proving F inverse is 1 1 or F inverse is on 2. So for proving F inverse is 1 1, we also prove that. So let A dash and B dash belongs to G, such that F inverse into A dash equal to F inverse into B dash. So we have F is onto function. So F is onto function in G. So we can take as two elements. So we take a two element A and B which belongs to G. So we define these two elements also such that A dash is equal to FA as per previous part, and B dash equal to FB. B dash equal to FB. So now we shall prove that F inverse is 1 1. So for proving F inverse is 1 1, so we can write down this as, uh, this can be written as, which implies that A equal to F inverse into A dash. This implies that B is equal to F inverse into B dash. So in this we put as A, or this equal to B. So we directly write down this as A equal to B. So when A equal to B, so we can write down this as FA, because F is 1 1. So we reversely use the definition. When A equal to B, so then FA equal to FB. So FA equal to FB, so this means A dash is equal to B dash. So this implies that A dash equal to B dash. So it means that F inverse is 1 1. तो बेसिक कॉन्सेप्ट बहुत ज़रूरी है इसके लिए, अगर आपको प्योर मैथमेटिक्स पढ़ना है तो सारा कॉन्सेप्चुअल आपका चलना चाहिए. So third part we prove that F inverse is onto. So for proving F inverse is onto, so for onto means we take element of B. So consider as let A belongs to G. So then if we take function FA which is A dash, for every A dash is also belongs to G, because function is defined from G to G. Okay. So by definition of F inverse, So we take A is equal to F inverse into A dash. So F inverse into A dash, so there exists an element A dash which belongs to G. So such that we write down as F inverse into A dash which is equal to A. So that means this having the pre-image in A. So we can say that F inverse is onto function. F inverse is onto. So we can say that F inverse belongs to AG. So F inverse belongs to AG. So this is the third property. Now we shall prove that the fourth property. Fourth property is existence of identity. Existence of identity. Existence of identity. So for proving existence of identity, so let we take as function f which belongs to AG. So then we claim that I be any set which defined from G to G is 1 1 onto and homomorphism. So by setting we take as I of A which is equal to A. They give the same element. So A belongs to G. So for every A belongs to G. So now we shall prove that I is homomorphism. So we shall prove that I is homomorphism. So for proving I is homomorphism, I of AB is equal to AB by the definition. So this AB can be written as I of A into I of B. So it means that I is homomorphism. I is homomorphism. Now to prove that I is 1 1. So for proving I is 1 1. So for proving I is 1 1, so we can write down as I of A is equal to I of B. So I of A means A equal to B. So directly we can say that I is 1 1. Now third, I is on 2. So I is on 2. So for proving I is on 2, so we take the element of second set G. So let B be the element of G. So then there exists an element, then there exists an element B which also belongs to G. So such that I of B is equal to B. So because function is defined from IA equal to A. So I of B equal to B. So we can say that I is onto. So I is onto. So that means I belongs to AG. So I belongs to AG such that f of IA, f of IA is equal to f of I into A is equal to FA. So f of I, f of I is equal to F. So f of I equal to F, or when fi equal to F, so if is also equal to F. So if equal to F, so then we can write down a change. If is also equal to F. So then I belongs to AG. So hence AG is a group.